Good morning, everyone. We from Group K10 would like to present our final year design project, which entitled Production of Aviation Fuel from Plastic Waste (LDPE). Among the available resources, plastic waste is chosen as the raw material for the production of jet fuel. The reason is because only 9% of plastic are recycled and the remaining 81% of it end up in incinerations and also landfills, which had created tremendous negative impacts towards our environment. For jet fuel specification, the type of jet fuel that we choose to produce is Jet Air 1, which is the most common fuels that used around the world. The standard that required to fulfill for Jet Air 1 follows the DEF stamp 1991, ASTM specification D1655, and also IATA guidance material crossing type NATO code F35. Since the jet fuel consists of hundreds of chemical substances and also additive, the jet fuel component is simplified and summarized as table below. So, the main component of Jet Air 1 consists of group alkyl aromatic, branch paraffin, and paraffin and also naphthalene. The component for each group of the chemical substance is also listed in the table below, which is 1,2,3,4-tetramethylbenzene, 2,3-dimethylundecane, endodecane, and also heptylcyclohexane attached with the percentage of each component respectively. The physical and chemical properties of jet fuel is also listed in the table shown in the slide. The global supply and demand for sustainable aviation fuel is shown in the graph attached in the slide. Our production plant is expected to start operate in 2025, and the global shortage of jet fuel in 2025 is foreseen to be 970 kilotons per year. In order to cover the shortage in Asian and Australia regions, 48.5 kilotons per year of jet fuel is required. The production time of our plant per year is 330 days. The production flow rate for jet fuel is expected to be 6,500 kg per hour. The raw material, which is the LDPE required for production, is 76.89 kilotons per year. The table shows the production capacity among the competitors, where our production capacity lies between Red Rocks Biofuel from US and also Nestle from Finland. This shows the raw material availability in Malaysia, where the supplier being chosen for the production of jet fuel plants is Model Plastic Recycling Sdn Bhd with the supply ability of 661.2 kilotons per year. Catalytic pyrolysis is chosen to be the reaction for the production of jet fuel. The reactant and product produced during the reaction is listed in the table. Economic potential curve level 2 is constructed based on the formula cost of the product minus cost of the reactant. As we can see in the graph, the conversion starting from 0.4 until 1 shows a reasonable profit generated by our plant. Here show the process design level 3, where the important information and criteria of reactor is listed in the table. The installation cost and annual cost of the reactor with respect to each conversion is also calculated and performed in the table. The economic potential curve level 3 is equal to economic potential curve level 2 minus the cost of reactor. Process design level 4 review the separation unit used in the production of jet fuel. Economic potential level 4 is calculated by using the formula economic potential level 3 minus the cost of separation units. From the graph, it can be seen that the gross profit of our plant increased drastically from 0.1 conversion until 0.8, and starting from 0.8, the gross profit starts to flatten. Hence, the optimum conversion, which is 0.8, is chosen to be the design conversion for our plant.
Okay, next is the process flow diagram for our plant. We have three processes, which is the first one is pre-treatment process, where we have shredder, washing tank and dryer, which is rotary wheel dryer. After that, we will go into the second process, which is reaction process where we use fixed separator and our catalyst is ZSM5, and it will go into the last process, which is separation process, where we have flash drum and 3 distillation column where we want to separate our product, which is jet fuel, and from byproducts such as N-hexadecene and N-octacosine, and also from gases such as methane, ethane, nitrogen, and hydrogen. Next is the PFD after heat integration. This is our PFD after heat integration. Before heat integration, we got 3 cooler, 2 heater, and the energy requirement is 436.7 kilowatt. And after the calculation, we got only 3 cooler and the energy requirement is 343.18 kilowatt. So we can calculate that the total energy recovery is about 21.42%.
Piping and instrument diagram are used to depict instrument and piping details along with the design of precaution to keep a safe level of control. And for the control strategies, it is to ensure the safe plant operation, achieve production plant, product quality standard, and lower the cost. The pipeline sizing was calculated for liquid, gas, and mixer stream. As you can see in the PNID diagram, the red stream is referred to the hot stream and the blue stream is referred to the cold stream. Next, for our process control, we have washer, we have dryer, we have reactor, flash drum, distillation column, storage tank or oil tank, and also cooler. For example, for oil tank, we use analyze indicator. For cooler, we use temperature controller to reduce the temperature, which is the set point is 50 degrees Celsius, and we use clock valve. For the pressure relief system, we have fixed bed reactor, flash drum, storage tank, and also distillation column. The pressure is 250 and also 350. Our flow destination is flow to flare.
Hazard identification involves the process of identifying and explaining hazards by characterizing their likelihood, frequency and severity, including possible losses and injuries, and assessing adverse effects. Table below shows chemical properties involving hazardous properties such as flammability, corrosivity, reactivity, and explosiveness. Each of the identified chemicals has their respective exposure limit that is assessed by occupational safety and health administration. From this table, it shows that the methane, ethane, and tetramethylbenzene are highly flammable. Thus, these chemicals are handled carefully. HIREC is the short form of Hazard Identification, Risk Assessment, and Risk Control. The objective is to provide a safe workplace to employees and people associated with the chemical plant. The table below shows the HIREC for a reactor. From the table below, it can be concluded that the high-risk hazard scenario is overheating, which is cause the tank vessel explode. The preventive measure for this scenario is perform scheduled inspection on temperature controller. Related acts and regulations. There are 4 main acts and regulations are included in this plan, which is OSHA 1994, Factory Machinery Act 1974, and Petroleum Safety Measure Act 1984, and lastly Environmental Quality Act 1974.
Next, selection of plant location. We have chosen the location based on the highest score, which is 74/90. The location is at Kawasan Pembentangan Tanjung Lansat, Pasir Gudang, Johor. The area is 3 acres with a price of 2.9 million ringgit. The main raw material supply are Gold Mine Polymer Enterprise, Hang Hab Industries Sdn Bhd, and Alba Polymer. The residential distance is 10.8 km. Labor availability is from residents of Kampung Sri Makmur, and the population at Pasir Gudang exceeding 1.145,639,000. The power supply is TNB electric substation, water supply from Syarikat Air Johor Sdn Bhd, airport facilities is Senang International Airport, and highway facilities is Johor Port Pasir Gudang. Next, plan layout of our location. Main gate, car park, wastewater treatment are placed at the upwind, while product storage that may spill flammable liquid is placed downwind to reduce loss of potential from an explosion of fire. There are 2 entrances to the plant. First main gate is for visitor and worker, while the second one is access for loading truck. Next, there are emergency response team to ensure safety of all and assembly area for worker to gather when unwanted event occur. Pre-treatment and main process located near to each other to
ease the transfer of raw material supply and reduce the cost of piping. Maintenance workshop is built near to the production plant and wastewater treatment for easier maintenance work for process units that need to be repaired.
Next is the waste inventory. The table shows type of waste in our plant, which is wastewater and water vapor. Next is the waste minimization. We decided to reuse the wastewater in our plant, and also the biosolid from the wastewater treatment can be sold as the fertilizer. Okay, next is the waste related law and regulation. There are two related law and regulation. The first one is the environmental quality in the industrial effluent regulation 2009, and the second one is the environmental quality schedule waste regulation 2005. Okay, next is the wastewater treatment plant, where our wastewater will go into the first tank, which is equalization tank. The BOD, COD, and suspended solid is shown as a table. And after that, it will go into the coagulation tank and flocculation tank. And after the treatment, it will go into the primary clarifier, where the sludge will go into the sludge tank, and the wastewater will go into the next step, which is aeration tank. After the treatment in the aeration tank, it will go into the secondary clarifier, where the remaining sludge will go into the sludge tank, and the wastewater that we treated, the BOD, COD, and suspended solid is shown as the table. And the chemical label standard is standard B, which is our treatment plant reached the standard.
Next, the economic analysis. Firstly, total capital investment included fixed investment capital, working capital, and land capital, while total production cost included direct manufacturing cost, fixed manufacturing cost, total plant overhead cost, and general expenses. The total production cost for our plant is 283 million per year. The design life is 20 years. Taxation rate for Malaysia is 25%. Scrap value is 0.584 million. Annual depreciation cost is 0.555 million per year. Minimum acceptable rate of return mark 15%, and sale price of jet fuel is 6.72 ringgit per kilogram. Next, summary of the profitability analysis. It is divided into two. Firstly, does not consider time. The second one is consider time. The value for return of investment ROI is 63%. Payback period is 1.56 years. Net present value is 228.07 million per year, and the value of net discounted cash flow rate of return is 0.44. Next, break-even analysis and capacity. The proposed plant capacity is 51,480 tonnes per year. Break-even point value is 80,000 tonnes per year. The proposed plant capacity is more than break-even point value, and this shows the profitable plant. The total income and total expenditure in the design plan at full capacity is considered to determine the break-even point, which is at 11 months. Next, sensitivity analysis. The sensitivity value shows the relationship between the input and output. The inputs are depreciation, direct cost manufacturing, land, and working capital. The plant is projected at 25% increase or decrease from the NPV value. Based on the plot shown, our plant is still profitable. Working capital and depreciation have least effect on the NPV, while direct cost manufacturing and land capital have greatest effect on the sensitivity analysis.
The conclusion is our plant is producing jet fuel using LDP plastic as the raw material which involves pyrolysis process. Secondly, our plant is selected to be in Pasir Gudang industrial area due to its competitive advantages. And then the economic analysis shows that our plant is profitable and considerable. And then the sensitive analysis is also carried out to prove that the profit of our plants is robust. And the plant of capacity is 51,480 kg per year.